And so let's talk about the mathematical universe. So the mathematical universe really, it just consists of the mathematical objects you'd like to talk about. That's why it's also called the universe of discourse. And mathematical objects, we can also just call them values. And so what kind of values are we talking about here? Well, numbers, sets, functions, truth values, booleans, programs, vector spaces, really anything mathematical. And yeah, so really the limit is your mathematical imagination here. So, well, mathematical objects are fine, but they're kind of boring if you cannot do anything with them. And that's where operations come in. So operations are for combining values. And when you apply an operation to n arguments, then this results in another value. So an operation on the mathematical universe U has an arity, n, and the arity says, okay, I'm accepting n arguments, and each argument is a value, and the output is going to be, again, a value of the universe. And so you can imagine that a value is just an operation of arity 0, because a value is just an operation that doesn't accept any arguments. And well, that's of course a well-known thing. So a universe, together with a finite number of operations, that's also called an algebra or an abstract algebra. And here's a simple example. A Boolean algebra. The universe consists of just two elements, 0 and 1. There are just two values in our mathematical universe. And there are various operations I'd like to point out, like true, false. They both have arity 0 because they're just values. Not is a unary operation, and and or are binary operations. And well, what are the mappings that they represent? That's kind of clear. True, for example, can be 1, false can be 0, and so on. Another example is a calculator on the integers. So our universe is the integers now. We have operations 0 and 1. These are again constants. And we have operations plus, minus, and multiplication, mal. And these are all binary operations. And yeah, that's very simple, of course. So now we'd like to add division to our collection of operations. And well, here we have a small problem that, for example, division by 0 is not really defined, right? And well, this is supposed to be a very simple calculator, so we also cannot divide 12 by 7. That is also not defined for us. It's also an error. Well, if we want to deal with this in our framework of universe and operations, if we want division to have as a result an error, for example, when dividing by 0, we have to add that error to the universe. And so let's just do that. And so our universe now is the integers plus an extra error value. And then we can just say that 12 divided by 0 or 12 divided by 7 is error. And well, of course, now the error is part of our universe, and that means we also have to say, okay, what is, for example, error plus 4, right? And well, the simplest answer for that is each time an error is one of the arguments, then the result will be automatically an error too. So that's an easy convention we could choose here for our calculator. All right, so we have values, we have operations, and so now Cantor's theorem tells us that there are many more operations than values. And so really the details of Cantor's theorem are not that important. I've written them up here on this slide just to show that both the statement and the proof is very short. But really the consequence is just there are really many more operations than values, and that's just a fact we cannot change. And so when we ask ourselves now, are operations also mathematical objects? Then in general, Cantor's theorem tells us no, that cannot be, because there are many more operations than mathematical objects, so this cannot be the same. And well, if we are in denial of this fact, or we somehow try to work around it, then we could try something like this. We start with an initial universe, U0, and then we consider all the operations on U0 and things like products and so on, and we form a new universe U1. And of course there will be again operations on U1, so again we add them and we arrive at U2, and so on. So we can do this infinitely many times, and we could say, okay, that's not a problem. We just form the union of all of this, and we arrive at the universe at level infinity, right? And well, obviously this doesn't really solve anything, because we're still basically where we started. We're just at a higher vantage point. There are still operations that are not in our worldview now, the operations on the universe at level infinity. So our mathematical universe is not complete. No matter what we do, if we work in this way by trying to construct towers of universes, we will not reach the entire mathematical universe with this. So the consequence is easy. I'd say don't try to turn operations into mathematical objects, because if you do, you will either limit the universe you can talk about, or you will run into paradoxes. And well, so, but we still need a way to talk about operations, right? If we don't turn them into mathematical objects so that we can talk about them, we have to find another way of talking about operations. And this other way is operators. So operators on a mathematical universe, they're combining operations, and they again result in a value. So that's very similar to the idea of functionals. It's a very common idea in mathematics, in functional analysis, for example. It's really the same thing. It's just that you're not operating on a particular vector space now or something, but you're operating on the whole mathematical universe. So an n-ary operator on the mathematical universe is a function that accepts n operations as inputs and yields a single value as its output. Okay, and so each of these n input positions, we can only so an operator accepts like only operations of a fixed arity in each of them. And so if there are n input positions, then you have arities m1 to mn, and this list of arities we call it the shape of the operator. All right, and now a simple extension of the idea of an algebra or abstract algebra is an abstraction algebra. And so an abstraction algebra is just a universe together with a collection of operators on U. And so here, as a picture again, we've already said that every value is an operation, right? Another operation, and in turn, every n-ary operation is also an operator, right? Because we can just see that an operation takes n arguments, and each argument has arity 0 because it's just a value. So the shape of an operation is just a list consisting of n zeros. And in particular, a value then is just an operator of the empty shape. And so values are operations, and operations are operators, and so we arrive at this picture here. So, but on the other hand, let's be clear that although some values are operations, operations in general are not values, and of course operators in general are also not values either. Let's return to our example, a calculator on the integers. And so previously we've seen the operator 0, 1, plus, minus, mul, and diff. And now we're adding further operators, not only operations but general operators to it. The sum operator, which takes 3 arguments. The first 2 arguments are just a lower bound and an upper bound. These are integers. And then we also have an operation f. And the sum just sums up all values of f between the lower and the upper bound. And so the shape of the sum operator is 0, 0, 1, because L is a value, U is a value, and F has arity 1. And very similarly, we could imagine an operator prod for product, which has the same shape as the sum operator. And it does the same thing, but it doesn't sum up the values of f, but it multiplies them with each other. And as a generalization of these 2 operators, we could, for example, imagine an operator iter, which generalizes what we are actually doing here. Are we summing the values up? Are we multiplying them? And we're abstracting this by a binary operation g. And iter takes this binary operation as an argument and performs the same thing that also sum and product would perform. So you see, there is nothing mystical or something behind operators. These are everyday occurrences that appear all the time when we do anything practically, like computing or programming or whatever. And again, just to compare these 2 worldviews or mathematical views, well, this is a view of type theory, right? You have this universe, these towers of universes, and what this does is, though, it restricts your worldview to some sub space of the entire mathematical universe. On the other hand, in abstraction logic, we say, okay, we are looking at the entire universe, and the entire mathematical universe, and then in addition we have operations and operators on the mathematical universe. And well, the only price that we're paying here is that operations and operators are not mathematical objects. Yeah, but there is really no way around this due to Cantor's theorem.